Hello all. I'm going to take the concept moving coil galvanometer from the chapter Moving Charges and Magnetism, class 12 physics. So what is a moving coil galvanometer? A moving coil galvanometer is an instrument used for the detection and measurement of small currents. So that's the purpose of why we use a moving coil galvanometer. Now, what's the principle of a moving coil galvanometer? Its principle is very simple. It's on the fact that when we place a current carrying coil in a uniform magnetic field, it experiences a torque. So, what's a torque? A torque is a rotational force that comes into play when a current carrying coil is placed in a uniform magnetic field. So with that principle, we are working the moving coil galvanometer. So now let's see the construction of a moving coil galvanometer. The moving coil galvanometer has a rectangular coil consisting of number of insulated copper wires. Now this rectangular coil is bound over by a non-magnetic metallic frame. This coil is suspended by means of a movable torsion heads connected by a phosphor bronze strip, which is placed inside a uniform and strong magnetic field by means of two cylindrical pole pieces. So it's placed in a strong magnetic field produced by two cylindrical pole pieces. Now the lower end of the coil is connected to a hairspring, and there is a soft iron core which is placed inside this coil, where the coil does not touches the iron core, nor does the coil touches the magnetic field. So since the coil does not touches the iron core and the magnetic field, the coil is perpendicular to the magnetic field. That is, the plane of the coil is perpendicular to the plane of the magnetic field. Lastly, the construction has a concave mirror which is placed inside this instrument, which helps us to note the deflections that are happening inside the instrument. So that's all about the construction of the instrument. Now let us come to the theory of the moving coil galvanometer. Now let I be the current passing through a coil of length L and breadth B, having a strong magnetic field. So, as we said the principle, when a current carrying coil is placed in a uniform magnetic field, it experiences a deflecting torque. So, we represent the deflecting torque tau as NIBA, where N is the number of turns, I is the current, B is the magnetic strength, and A is the area. So, a deflecting torque happens. So, when this deflecting torque comes into play, the coil rotates. So we have to first remember that this coil is connected to a phosphor bronze strip. So when the coil rotates, the phosphor bronze strip gets twisted. When this twist happens, a restoring force comes into place. So first we need to know what's a restoring force. The word restore means to place something from its original position and take back it to the original position. So here also the restoring force means it takes back the coil back to its original position. So when this twist happens, an angle is made. That angle we keep as theta. So theta is the twist produced in the strip by the rotation of the coil. We represent K. K is a value that we represent as the restoring torque, which is the restoring torque per unit twist. So we can write restoring force is equal to restoring torque per the twist, that is K theta. Okay. So when equilibrium happens, both the deflecting torque and the restoring torque will be equal. So we can write deflection is equal to tau restoring force. So we can write NIBA is equal to K theta. So if we keep I on one side and take all the arbitraries to the other side, we will get I is equal to K by NBA theta, where K by NBA is equal to G, which is the galvanometric constant. So we get I is equal to G theta, where we can write I is directly proportional to theta. So that's the theory of moving coil galvanometer, and that's all about the moving coil galvanometer. Hope you all understood moving coil galvanometer. Thank you.